Yeah, hi Karthik. Am I
Actually,
audible?
yeah,
My screen is visible, right?
yes,
Okay, fine. So let's start. Okay. So in the last session, so we have started understanding support vector machines, right? So let's have a quick revision, and then we will continue from there. Okay. So to start with, we have seen what is a support vector machine. Okay, and then we understood why it's called support vector machines and what are support vectors. Okay. So the basic idea here is also to do a classification. Okay, since we have seen logistic regression. Okay, and the next algorithm we saw is support vector machine, and here to do the classification, that means basically to divide different classes. So there, as I was saying, in the linear logistic regression, it was a line. Okay, but here we generalized it and we started with a plane. Okay, and we call it as a hyperplane. Okay, it could be like any dimension, 2, 3, 4, 5. Fine. And the idea was simple: to find out, okay, two support vectors. Okay, and then draw a planes parallel to each other. Okay, and bisect them will give us the maximum margin line. Okay, I mean maximum margin hyperplane, and this distance is called as maximum margin. Got it? Okay, and
yeah,
then we
yeah,
have seen the we have understood like the basic equation of a plane. Fine, and we saw some vector related stuff, and finally we understood, we derived that the equation of a plane, okay, will be W transpose X plus W not equal to 0. Okay. Now, what are these W's? W's are our coefficients. Okay. I mean, for example, if you see, uh, if you are having two features, okay, if you are, okay, I mean, if your input is having two features, so obviously your line equation or plane equation will be W1 x1 plus W2 x2. Okay. And this is intercept equal to 0. So for each input feature, you are going to have some coefficient. That means how much that particular feature is contributing. Okay, so that is going to be dictated by this coefficient. Just like even in linear equation also we saw the line equation, right? Mx plus b or w1 x1 w2 x2 like that. Okay, so
yes,
here also we have this. So these w's, so over here the simple form we write is w transpose x, and assuming if it is passing through origin, then the equation of the line is w transpose x equal to 0. Okay, now that means what, here we understood an important thing, that this, see, even if you don't understand the derivation of this, that is fine. Okay, as I told you, finally you will be writing code, and code is extremely simple as far as machine learning is you go considered. Okay, so in case if you don't understand the complete max is also fine, but at least the main concepts like what is the equation of line, even if you don't understand derivation also, what is the equation of the line and what is this actual how to intercept this particular equation, if you try to understand, that is also fine. Okay, so when I'm saying W transpose X equal to 0, now what is W? W is our features, I'm sorry, coefficients. Okay, I mean W1, W2, W3, and X is what? X is the input features. Okay, X1, X2, X3. Okay, and X1 could be, as I said, age, X2 could be income, etc., etc. Now, when we are saying W transpose X equal to 0, okay, that means what? We saw that if two vectors, okay, if W and X are two vectors and facing W transpose X equal to 0, that means we can write this as mod of W into mod of X, okay, cos theta equal to 0. That means if two vectors product, okay, dot product is 0, that means they're perpendicular to each other. Okay, this is simple vector rule. Fine. So now when we are saying W is perpendicular to X, that means what? In the plane in which our X is present, I mean the input features, whatever the plane you are having, right? The coefficient plane is perpendicular to that,
correct.
right? Clear?
Yeah,
So
yeah,
you consider X. Okay, X could be not like, X could be like combination of three or four features. Okay, one, two, three features. Okay, and but the overall plane. Okay, if you consider that hyperplane of X. Okay, X could be three features or two features. Okay, so that means it will be three dimensional, four dimensional. Okay, to that particular plane, that W plane will be a perpendicular plane. Only then you will have this product as 0. Okay, so that is what we are understanding from this equation. Fine. Now coming back to SVM, so we just understood the plane equation. Okay, now we came back, and then what we did. So since we understood the basic equation of plane, so we can now assume few things. Okay, so what we said, I will consider one equation, the equation of this particular plane is W transpose X plus B equal to 1, and another plane equal to -1. Okay, and the middle, the maximum margin hyperplane will be 0. And why 0? Because this will be in almost in the middle of these two planes. Okay, so that's why I consider one distance as 1 and other distance as -1. Okay, considering one as positive set and other thing positive set and other the negative set. Okay, clear?
Yeah, yeah, clear.
Okay, then after that what we have saw, so instead of having two equations, so what we did, we multiplied with the actual label. Okay, yi into the equation of the line is greater than or equal to 1. So instead of 2 and 3, so we have only clubbing 2 and 3 points, we have only single equation. And in this equation, if you have positive class, so this will become W transpose X plus B greater than 1. Okay, so if I just take my pen, yeah, so if this is 1 for positive class, this is 1. Okay, so if you take that, so this is W transpose X plus B is greater than 1, you will get this one. And for negative class, when you do minus, multiply with minus, so this will become less than or -1, so this is this. Okay, so clubbing 2 and 3, you got this equation. Okay, so this is representing our planes.
Yes,
Agree? So
yes,
earlier, equation 2, equation 3 are separately representing two planes. And why are these planes important, Karthik? Because if you find out these planes, okay, see, this is a main point. So we are focusing on that points, okay, support vectors. That means if you are able to do justice to that point, all the points to the other side of this particular plane are automatically getting justified. Agree?
correct,
Right? So,
correct.
I mean, it's a simple analogy. If you see, if you have a door and if you need to pass through, okay, if the maximum tallest guy in the room, if he's able to pass through, automatically every other person will be able to, right? Because everyone will be shorter than him.
True.
Same,
Yeah,
like same that way. So if we are able to correctly classify this person, okay, who is very clear to the other class, then obviously all these are in safe place, right? Because anyhow these are more farther to these points when compared to these points, the support vectors. Okay, so that's why we are focusing on those points. Fine, so we combine these two points, planes, and we have this one single equation. Okay, and assuming this is going to work only when, okay, there are no
yeah,
missing of the points. Okay,
correct,
that means
correct. Both the
eh,
points are
yeah,
like
both should be
equally
perfectly classified. That means there should
correct.
not be any overlapping between positive and negative points. Only then
Correct.
this will satisfy. Okay.
Yeah,
Now, when we, yeah, so our aim is, so why we are doing all this, why we are studying all this, the only thing is to find out these two planes. That means such that the distance between these two should be maximum.
yeah,
Okay, maximum distance. Okay, if you don't want maximum distance, I don't, you can simply do some experiment and find out some plane like this. Okay, this is also dividing these 2 points. Okay, but this is not the best line. Okay, so
yeah.
we want the line with the maximum distance. Now, what is this distance d1? What is this distance d2? Okay, so we have the overall distance. Okay, we subtracted this from that. Okay, and we have seen this equation. Okay, and finally we have seen that the magnitude, sorry, by dividing this by magnitude, this will become unit vector,
Hmm.
right? So I think the other day I was also um, oh, sorry, why this is not open? 1 second. Oh, um, just give me 1 second, let me reopen this.
Yeah,
Yeah, the assumptions. Yeah, in the assumptions, yeah, over here, I have discussed shortly about vectors, right? So what
correct.
does a vector mean? So if you are having a vector A, which is saying 3 comma 4, that means in one direction its length is 3, in another direction its magnitude or length is 4. Okay,
Yeah,
so the length will be square root of each 3 square plus 4 square. If you have
correct,
3, 4, 5, or for
correct.
example, or you have like you have 10. Okay, you have for example some 16, you have 5, and you have 4. So it will be square root. You need to square each of these and do a square root of that. Okay, so
Hmm.
to get the
Hmm.
magnitude. Okay,
Correct.
and now to find, so that means what? So one important point I told you is, see, a vector will have magnitude and direction.
Direction.
Okay, so now for example I'm saying this is a direction of a vector. Okay, in this direction you can have okay, infinite number of vectors with different magnitudes, correct?
Correct.
So one magnitude, a small vector could have magnitude of 1, length 1, 2, 3, like that. You can have n number of vectors. Agree? All of these n vectors are sharing the same direction, but the magnitude is different. Agree?
Hmm. Hmm.
Okay.
Yeah.
So now, if you want to find out a unit vector, that means what? When I'm saying a unit vector of particular A, I'm indirectly saying, hey, I want a vector which is in the same direction of A. Okay. But magnitude is 1.
Hmm.
Okay. The magnitude of A could be anything. I don't
Correct.
know. Okay. But I want that direction, but with
Yes.
magnitude of 1. So to do
Correct.
that, what I said, so you need to divide
Divided by.
particular A by the magnitude of A. Okay,
Correct.
when you do this, you will get a unit vector. So unit vector is 3 by 5 by 4 by 5. Why? Because when you try to find out the magnitude of this, you need to do this square root of 3 by 5
Correct.
square plus 4 by 5. So just like how did it 3 square plus 4 square, right? So
Yeah.
you get 1. So this is proving that the magnitude of this vector, this is a unit vector.
That
Okay,
magnitude is 1.
magnitude is 1. Okay, so now, so why we studied this? Because here when we yeah, so when we have this equation, okay, one sec. Yeah, so when we have this equation, so we want this distance x1 minus x2, which is distance, right? So for this distance, so when we are dividing this, okay, this becomes 1. Okay, now the x1 minus x2 is 2 by mod w, okay, or
Yes.
magnitude of that vector. Okay, so this is a distance between two planes. Agree?
Correct.
Now
Yes.
this is max technical, but let's try to understand what it is saying. So it is saying, so Karthik, it is saying, so there are 2 points, okay, scattered in the space. Now you can find out any plane, okay, you can find out different planes, okay. So that particular plane, okay, so we want, okay, we want that particular plane, okay. So we are finding the equation of this, okay, we are finding the equation of this plane. What is this maximum margin plane? Okay, we are finding the equation of this plane. Okay,
Yes.
and also we had this question. So actually we want this. Okay, but why are finding this? Because it is easy to find out equation of one plane instead of finding two planes, right?
Yeah. Yeah.
This we can easily find out these planes if you want. Okay, but we are finding the equation of this plane. So the meaning of this is, you take any plane, that plane will have some equation, let's say w1 plus w1 x1 w2 x2 plus w not equal to 0. Two
Mm-hmm.
features. Okay, now you have this w1 and w2. So from that you can calculate this magnitude of w, that means square root of w1 square plus w2 square.
Yeah.
Okay, so that should be maximum.
Hmm.
um Oh, no, that should not be maximum. That should be minimum, because this overall should be maximum. 2 by overall should
2
be
double A double A.
maximum. The denominator should be minimum.
Okay.
Okay.
Yeah. Yeah.
So this is my distance, Karthik. Okay. So if you see
Okay.
the, this is my distance. 2 by mod W is distance. Okay. Now this
Okay.
distance should be maximum. Obviously,
Yes.
because if the distance is maximum, they are very well separated, right? So if
Correct.
that should be maximum, 2 is anyhow constant. So the denominator should be minimum.
Hmm.
The more the denominator is minimum, the higher the overall value will be maximum.
Distance. Yeah.
Correct. So we want that plane. So if you give me 3 or 4 planes, okay,
Mm-hmm.
so I will choose that plane which is giving me
The maximum distance.
the maximum distance. That means whose magnitude when divided by 2 will give you the maximum
Minimum.
value. Okay,
Yeah. I mean,
but
W
such
is
that
minimum. Mm-hmm.
this will work with this
Only
equation.
two
So this is
separable.
called as a conditional equation. Okay, this is
Okay.
not by direct equation. So this will work only when this equation, oh sorry, this condition is true. That means for every point, okay,
Mm-hmm.
when you do its class, okay, yi, that means it could be positive +1 or -1, correct? So
Hmm.
that yi into my w transpose. What is this w transpose from the equation? The whatever the line you are choosing, right? That
Yeah.
particular line transpose xi plus bi, whatever you are doing, right? This should be greater than 1.
Hmm.
If this is greater than 1, that means every positive point is in positive side, every negative point is in negative side.
Yeah. Yeah.
It is already there, but you just need to find a plane. That's it.
Correct.
The points are almost separated, but the plane you want,
Yes.
and that, like that you can have thousands of planes, but we are looking for that plane which will give the maximum distance.
Yeah.
Okay, clear?
Clear.
Okay, so that was the point. So, and because it is hard to find, okay, because it is hard to find the data where the classes are almost already separated,
Yeah.
right?
In real time.
It's
Yes.
called, it's that's why it's called SVM hard margin.
Okay.
Okay, this will work, but only when almost perfectly separable data. There should not be any misclassifications.
Yeah. Yeah.
Okay, so that is the point. Okay, but in real life, so I think till here we have discussed.
Hmm.
Okay, any doubts till here?
No.
Okay, fine. So now we we know the equation of the plane, and then we also know what should be the criteria we are looking for to
Hmm.
find out the that plane. That means this is a distance criteria and this is a equation. Okay.
Yes.
So now just for a moment, what we can do. So if you have patience and time, you can try with thousands of planes and calculate its distance. Make sure this equation is fitting. Okay. And if it is fitting and you have, let's say, 1000 planes, in that you can calculate this equation and find out the best plane from that, which is giving this value maximum. Okay. Manual way.
Yes.
Okay, fine. But obviously, we're not going to do that. We are going to use ML for that. But since we cannot have this, right, in real life, it's very hard to find such data. We have something called as soft margin. Okay. Now, if you see, okay, yeah. So this soft margin is called minimum of, yeah, so same thing. Okay. If you see here, we want this value as maximum 2 by mod W, right? Agree? In hard margin, what is our goal?
W value will be minimum, so that we will get the maximum value.
Correct. The reverse. Okay. So
Yeah.
we want this to be the maximum. So in this is a hard margin equation,
Hmm. Hmm. Hmm.
Karthik. Okay.
Correct.
In soft margin, what happens is this is the equation for soft margin. So here, what happened, if you see, we want minimum of this. Okay. If you want maximum, the reverse will be minimum. Okay. Minimum of W mod square by 2 plus C summation of eta I. Okay. So this is some, okay, Greek letter. Okay. Eta I. But what is this? We are going to see. But I think in the previous session itself, I explained you here we have W. Okay. Why we are using W square here. Okay. So it is easy to find out the, okay, minimum value when compared to maximum value. Okay. See, if you have an equation, okay, to find out the maximum value is one thing, or to find out the reverse of it, minimum value is different. Say, are you getting? See, what I'm
Yeah.
saying is you are having 2 by W.
Yes.
Okay. Finding the maximum value of 2 by W is same as finding the minimum value of W by 2.
Okay.
Right? Because if this is maximum value, okay, if you want, if you are trying to find maximum value of this, if you reverse that, you want the
Mm-hmm.
minimum value.
Okay.
Correct? So similarly, in the soft margin, what happens is minimum of W square. Okay, instead of W, I'm using W square by 2 plus we are adding a some more term. Okay, this is kind of regularization equation if you see. Okay.
Okay.
So
Okay.
I'm doing this. But one question is, instead of W, why we are using W square is
Yeah.
here we are finding minimum value. Okay. So it is always easy to find out the minimum value of a square function. Okay. Because square function, it is differentiable. Okay.
Okay.
Because when you do x square differentiation, you will get 2x.
Okay.
Okay.
But
But
a
x,
square will give maximum, right? Value, W value. Square will give maximum W value.
correct. But what I'm saying here is,
Mm-hmm.
uh, I think I have, did I explain you over there? Huh. See, you are right. So what will happen here is you are having, for example, x, okay,
Mm-hmm.
and x square. Okay, this value, okay, you want to find out the minimum value.
Okay.
You want to find out the minimum value. X square will give you the maximum value, okay, when compared to
Mm-hmm.
x. That is
Yeah.
true. Okay.
Mm.
But you want to find out the minimum value of x square. Okay.
Okay.
Minimum value of x square. X square,
Okay.
you can put different values of x square, right? So x square could,
Hmm.
if you put 2, it will become 4, 4, 8, etc. Okay.
Yeah.
In our situation, okay,
Mm-hmm.
like that, like using, like wherever this condition is satisfying, okay, so in that particular situation, so which particular W square you are having w square by 2, you are getting minimum. Okay,
Yes.
which particular plane you are getting minimum value of w square. But now
Okay.
your question is x square, you will get maximum when compared to x. Okay, but we are not trying to find out maximum value, we are trying to find out the minimum value. Okay, how you will get the minimum value? Okay, you have this, when you differentiate a function and equate it to 0, you will get the minimum value. Okay, so when you, how to find, see for example, if I show you, okay, this simple max. Okay, so uh, minimum value of a function, this is actually we studied sometime in the ninth class max. Okay, the lowest value, uh, yeah, so when you see here the derivative of the function, set it to 0 and solve, these are the called critical points or also the minimum values. Okay, so that means what, when you do the differentiation,
Mm-hmm.
okay, and equate it to 0, okay,
Yeah.
there you will find out the minimum value.
Okay.
Okay, so but to mean, but to do the differentiation, okay, the function should be differentiable. Okay,
Yeah.
so that's why we will take functions like x square, x cube,
Okay.
easily, which we'll be able to differentiate. Okay,
Okay.
because if you take x, okay, it will be able to differentiate. Okay, you will get 1. Okay, but after that you will get 0. Okay,
Yeah. Constant. Yeah.
constant. Okay, but that's
Yeah.
why usually, okay, I also got this doubt actually, so that's why I googled. So here it is saying the square function is w square is differentiable everywhere. Okay, making it easier and cleaner to apply calculus based optimization. Okay, so because the derivative of w is not defined at 0, it seems. Okay, so the derivative of w is not defined at 0. So okay, the mod function derivative, if you see, I think you will get something like this. Okay, at 0 it will be undefined, but for the square function, okay, it will be like this. Okay, oh, for example, if you see, square function graph, yeah, you see this. Okay, what is differentiable means, you will be able to draw a tangent. Okay, so these are simple max, Karthik. Okay, so if you are getting confused, what I'll do is, let me see if I find out a tangent. um yeah, so for example, if you see this point, okay, if you see this
Okay.
point, so anywhere if you are able to draw a line, okay, if
Mm-hmm.
you are drawing to draw any, you take any point. Oh, sorry. Let me take pen. Yeah, as I said, SVM is full of max. Okay,
Okay.
so it's very less concept, just like, not like logistic regression. Here it is, the the concept is simple, but mostly involved with a lot of max. Okay, so
Yeah.
like equations. Yeah, so just a second. Yeah, for example, if you have a point over here, so what is the slope of this point? So yeah, so slope is, you will draw a line, okay, such that it is just touching that point, okay, over here, and this will be its slope. Okay,
Correct.
when
Correct.
you
Yeah.
touch points, you have a point here, so you will draw a line such that it just touches that point and do this. This is a slope. Okay, so it should be in a curve. So here is, you have a curve, so you can draw this. So that's why here it's a 0. Okay, so but if you see the mod function graph, yeah, so over here, yeah, it is not differentiable at this point. Okay, because we don't have any curve. Okay, so only when you have something curve, so you will be able to draw a tangent like this or like this. Okay, so but we have at the minimum point at 0, so this is not differentiable. Okay, so that's why usually what people do is, they consider w square. Okay, instead of minimizing w, they do w square, because that is much more differentiable.
Yeah. Got it.
Okay, fine. So yeah, this is just basic concept. Okay, but the equation which you have is this. Okay, the minimum value, instead of finding the w 2 by w distance, okay, what we are doing it is, we are having w square by 2, okay, plus c into particular equation. Okay, so this is the soft margin. Okay, that means what? We are okay with, we are assuming that there are some misclassifications. Okay, because it is hard to find out a perfectly classified data. So here we are saying it's okay to find out a little bit misclassifications.
Yeah.
Okay, but how many, how much, how far is the question.
Hmm.
Okay,
Yeah.
so we
True.
will see that. But before that, I'll just show you one scenario just to make the concept clear. For example, you have this particular scenario, Karthik. Okay, so you have this
Hmm.
dataset, and the idea is simple to divide this using a plane. Okay, and you can draw n number of planes.
True.
Okay, so on which one are you going to consider? Fine. So the one how you are going to apply here is, so if you see, for example, I'll just take a example of two planes. Okay, you can have any number of planes, but if you consider these two planes, if
Hmm.
you say equation of one plane is this, okay, and equation of other plane is this. Okay,
Okay.
why? Because you are having two features. I don't know how many features are there. Okay, assuming that there are two features, these are labeled classes. Okay, let's say this is positive class. Okay, this is negative class. This is positive class, and this is negative class.
Hmm.
Okay, now this is plane P1. Okay, plane P2. Okay, by looking, I think we cannot say. Okay, so because for these points over here, this is very nearby, and for this point, this is nearby. So I cannot say which is dividing this with maximum margin. In that
Okay.
case, what we have is these are the two equations. Okay,
Mm-hmm.
so now there are few steps. Okay, consider the general equation of the hyperplane, which is
Yeah.
W
Got it. Got it.
x1 W2 x2, right? After that, calculate the distance error function for each line. Okay,
Hmm.
so this is a distance. So that means what? So these are the coefficients. So for these, this will be square root of 2 square plus 5 square. Okay, the
Yeah.
coefficient square. Okay, and for this, it will be square root of 20 square plus 50 square.
Hmm.
Okay, so this we need to do. After the calculate the 2 by W. Okay,
Hmm.
so 2 by mod W. This is only mod W. Okay, so 2 by, I mean, 2 divided by this and 2 divided by this.
Yeah.
Okay, so I think this value is obviously greater than this value,
Here W value should be minimum.
right? Okay, so 2 by this is 25 plus 4 29. Okay, and this is 2 by 400 plus 2500,
2500. Yeah. 2900.
2900, right? So
Yeah.
obviously
First.
this value is
First one.
bigger. So this value will be less. Overall value, this overall value is less. Okay.
Hmm.
Now here this value is small value. That means this overall value will be big value.
Yeah.
And what is this overall value? This overall value is a distance.
Correct. Distance
So
between two.
this is
Yeah.
this is dividing the both points with maximum distance when
Hmm.
comparing these two planes.
Yeah.
Getting?
Yeah.
Okay. So this is how, even if you have 10 or 20 planes also, one way, okay, obviously we'll not do that, but just for your understanding how
Yeah.
what is happening. Okay, so if you have 10 planes, you will calculate this value. Okay, this is called distance error.
Got it.
Okay, so we calculate this and then we do by 2 by W, and whichever is having the highest value, so that plane is dividing with the maximum margin. Fine.
Yeah.
So that is for the hard margin. So that works. Now going back, since we understood hard margin, so now let's step into the real world scenario. In real world, as I said, it's very hard. So we have this equation. So now earlier we had this equation 2 by mod W, but we have a big equation. So what changed and why it is changed and how this is helping us. So we'll try to understand that in this class. Okay. Yeah. So yeah, I think that's a long revision. Okay, but I think you understood the concept, right? Till what
Yeah.
discussed now. Fine. So now if you see what changed from hard margin to the soft margin. So one thing is we changed maximum to minimum value because it's always easy to find a minimum value.
Hmm.
Correct. Second thing, we added C. Okay. See how many errors or misclassification that can my model have. Okay. So C is telling me. So when I'm saying soft margin, that means I am agreeing. Okay, there are possibility for some misclassifications because no model is 100% perfect. Okay, and it is very hard to find out the perfectly classified data points. Okay, so I'm saying okay even if there are some misclassifications also. Okay, but how many misclassifications, that is determined by my C. Okay, just understand the
Oh,
parameters. What is
yeah.
its effect, we'll see later. Okay,
Okay.
so now the main concept is we are saying okay, there could be some misclassifications. Okay, now when I'm saying misclassifications, you will get two questions. How many misclassifications? and how worst
Hmm.
misclassifications.
True.
That means this is hyperplane. Okay, this is a blue. If my blue point is to this side of this dotted line, it's very perfect. Correct? If it is started coming this side, okay, now blue line, still it is good classification, but not the best classification.
Correct.
Correct? Because this is my maximum margin plane. And if it is coming closer, here also it is classification, but not a perfect classification. If it is crossing this, then it is a misclassification.
Correct.
Now, if it is this, it's a very bad classification.
Correct. Like this, there are so many points.
Yeah.
There might be.
This is
Yeah.
also misclassification. This is also misclassification. Okay. But this is worst misclassification because if needed, if we just tilt this line a bit, this could fall into this. Okay. If this line becomes slightly like this,
Correct.
okay, we can save this guy. But this
Hmm.
guy is very far off. Okay. That means this guy is very badly misclassified. Agree? So
Yeah.
the distance from this margin hyperplane will also matter. Correct?
Yeah.
Getting?
Yes.
This is very important point. If you see, one very important point you need to understand here is this is maximum margin plane. For blue color point, okay, or let's say positive. So this is, let's say, positive class, okay, and this is negative. Okay. For a positive class, I don't care about, and this is left side distance. Okay, this side is left side distance, right? This side is right side distance.
Yeah.
Okay. For a positive class, I don't care about the left side distance from the maximum margin plane.
Hmm.
Okay. I only care the right side distance. Okay.
Okay.
That means if it is start moving, if it's crossing maximum margin plane, it is start coming here. That means right to the maximum margin plane, then that is issue for me.
Correct.
Okay. Left side, even so far, even any far also I'm fine. For the negative points, I don't care about the right side distance. I start caring the left side distance. Okay. That means if it is going to the left side and if it is, if the green color point, okay. So for example, if the green color point is here, okay, 1 point. Okay. So this is also can be called as good classification, but not the best classification because it is to the right side of this maximum margin plane. Okay. That's fine. Okay. But it is not a perfect classification. The reason is it is not to the right side of this support vector.
Correct.
Okay. Support vector is the line, okay, which we have considered to be the, okay, I would say foundational point, okay, to
Hmm.
create this plane. Okay. So if any point is getting misclassified, fine. So then we'll calculate the distance. Fine. So if we have a green point over here, it is a very bad misclassification. Correct? But if we have a green point over here, is that good or bad?
It's very.
If I have a green point here,
Yeah. This is fine.
this is fine, right? Very much fine. Very
Yeah.
good. Because perfectly classified, perfect classification.
Yeah.
Getting? So now the reason why I discuss these two are now there are 2 points. One is how many misclassifications? I mean the number 3,
Correct.
4, 5, 10. Okay. Second thing is the distance. How much is a misclassification? Small misclassification, big or very far misclassifications.
Yeah.
Getting?
And that varies point to point.
Yeah, that varies point to point. Correct.
Hmm. Yeah.
Okay. So that's why we are doing this summation.
Yeah.
Each point we are considering.
Correct.
Okay. That's a good question you asked. So the C will tell you total how many misclassifications it is happening. Okay. 10, 20, 30. Okay.
Hmm.
But as you perfectly said, for each, when I'm saying 20, so 20 are not doing same misclassification, right?
Correct.
Few could be very far or few could be very
Near
mild
to line. Yeah. Near to
classification,
that.
few could be very
Yeah.
worst misclassification.
Correct.
That's why we are doing the summation and for each and every point I'm calculating what is the distance.
Okay.
Okay. So when you are clubbing these two are regarding the misclassification. So when you are clubbing these two with the distance,
Hmm.
fine. So that is my new margin called as
Okay.
for SVM.
Okay. Got it.
Okay. Now
Hmm.
here we have two things. So one is C. C is going to tell you that how many errors it is going to have. That means how many misclassification does my model have. Okay.
Hmm.
And this zeta, this is called zeta. Okay. The value of this error.
Okay.
Okay. The value of this error. Okay. That means how much, what is the value, misclassification value. Okay. So now if you see the same equation I've written here, so my soft margin will look something like minimize this one w square by 2, okay, plus c, okay, summation of I, 1 to n zeta I, okay, such that here my equation is w transpose x greater than 1 minus zeta I. Okay, earlier we have 1, okay, for the hard margin, okay, we have this equation, right?
Yes.
Are you following? You are following,
Yeah,
right?
yeah,
Yeah.
yeah, yeah.
So this is a distance, but with a condition. Okay. Now, instead of 2 by W, we had a new condition, new equation,
Mm-hmm.
but with new condition.
Yeah.
I am using the zeta over here. Okay.
Okay, got it.
Zeta. Okay. Now, this a condition is zeta I should be greater than 0. That means distance should be greater than 0.
Hmm.
Okay. Even for this side also, that side also, the distance I am considering it as greater than 0. Okay. Now, two things very important. Okay. Now we are discussing the actual, the main area of the SVM. So when you see this equation, there are two things, Karthik. One is marginal error, one is classification error.
Yeah.
Okay. Marginal error is the same thing we have studied in the hard margin. Okay. So we are considering only like how far, okay, these two are getting separated.
Hmm.
Okay. The only I'm considering about that margin.
Yeah.
Okay. The distance between these two, this distance is there, right? This is called margin.
Yeah.
The same thing, yeah, this distance
Distance
maximize.
between distance between support vectors. Yeah.
Correct, exactly, that is fine. One more thing I have added, this is called classification error. That means,
Hmm.
okay, I'm
Um,
using the soft margin, but what is my from some error also I am accepting. Okay,
yeah.
but that is what classification, that so in the classification how many of them are getting misclassified, how much that is, it is getting misclassified, these things will come into picture.
Yeah.
Okay, a mixture of these two errors, okay, is our new soft margins
Correct.
equation. Okay. Now,
Yeah.
okay. Now, zeta is a non-negative class which refers to the degree of misclassification of each class. Okay. Fine. Now, let's try to understand this zeta. Okay. Now, if you understand these 3 points, zeta is very easy for you. So, if the data point is correctly classified and lies on or outside the margin, okay. So, then the distance will be 0. Okay. See, that's why if you see, Karthik, you are having this green color line.
Hmm.
Okay, that is our maximum margin hyperplane. Agree?
Yeah.
And this is my positive class plane. This is my negative class plane. Okay,
Yeah.
these are my, let's say, support vectors. Clear?
Hmm.
Now, for these blue points, I don't care about this distance, as I said, because this is
Correct.
good. Okay, I care about only this side distance.
Yeah.
And for my red points, I don't care about this distance. I care about only this distance because in this direction only there could be some misclassification.
Correct.
Correct? So clear. Now, if you focus, if for, for this blue point, okay, if you see this blue point, right? Okay, this is a distance from this plane.
Okay.
Okay, and this red point, this is the distance.
Correct.
Okay, now we are having a blue point. Okay, consider a blue point. Now a blue point could be here in this place. That is fine. Now this is my maximum margin plane. Now a blue point could be here.
Correct.
A blue point could be here.
Hmm.
Okay, if it is crossing this green line, it is getting misclassified.
Yes.
Okay, now if it is getting, we will consider that as misclassified, and the degree of misclassification is going to increase.
True.
Okay, and the degree of misclassification is going to get increased. We consider that. Now, if at all for positive class points or negative class points, if we have zeta equal to 0, that means the point is correctly classified.
Okay.
Okay, that means zeta is telling you about the misclassification distance, Karthik.
Correct. Correct. Got it.
Okay, so if that is 0, that means it is not misclassified, that is correctly
Yes.
classified.
Yeah.
Okay, that means blue point, that means you are talking about which points? These points,
Hmm.
and also these points.
Correct.
Okay, because these are where they should be.
Hmm.
Correct. So for all these
Correct.
points, the zeta is 0. That means there is no misclassification. Now, if you are having zeta is 0 to 1, okay, this distance is 1. This distance is also 1.
Mm-hmm.
Correct. The magnitude I'm talking, we consider this
Yeah.
as minus 1. Okay. Okay. but the magnitude is 1 and 1.
Okay.
Okay. So if the distance is between 0 to 1, the data point is correctly classified, but within the margin.
Yeah.
Okay. So somewhere blue points are over here and red points are over here.
Yeah. Because even finally that those are segregated by the midline. Yeah. So that is
Correct.
also fine.
Okay. So that is also fine. Not a perfect classification, but that is also correctly classified, but within the margin.
Margin. Yeah.
Okay. But if it is crossing that, if it is greater than 1, that means a blue color point crossing this and falling here, and red color point crossing this and coming here.
Yeah.
Okay.
That is greater than one.
That is greater than 1. That point is misclassified. Okay.
Yeah.
This is how you need to understand the value of zeta. Clear?
Okay. Yeah. Yeah.
It is talking only about the misclassification distance. If it is correctly classification, it doesn't care about it because anyhow the distance will become 0.
Correct.
So for this, can you tell me what is the zeta for this point?
I mean, red point, right?
Red point,
Red point is for 0.
0. For this
Hmm.
point,
For blue point, it's 0 only.
0, right? This point,
That is also red. That is also 0.
okay. Now if I have red point say here, what will be the
Mm-hmm.
value? Is it 0 or 0 to 1 or greater than 1?
It's a greater than 1 because that should be beside a green line. Though, I
Okay.
mean,
Now
in
if I
between
have
green
here,
and that is in between 0 to 1.
okay, perfect. Okay. So now you got the point. I'm happy. Okay, fine. So this is the value of 0. Okay. Zeta we understood.
Yeah.
Now let's try to understand C.
Mm-hmm.
Okay. C is, I told you how many misclassifications. It's like a regularization concept. Okay. So which we studied in the linear regression part. Okay.
Mm.
So now C is a regression parameter, but it is inverse of regularization.
Okay.
Okay. That means if you increase the value of C, okay,
Mm-hmm.
there is a small logic over here. Okay. So that means if you increase the value of C, that means you are decreasing the regularization.
Okay.
Okay. So, but what is fundamentally regularization, Karthik? So regulation is a concept which will help you to stop overfitting.
Yeah. Yeah.
Okay. So regularization, I'll just show you one definition. That's it. Okay. Nothing more. So if you go to the top, regularization is a set of methods of reducing overfitting.
Correct.
Okay. Just remember this line, nothing more. Okay.
Mm-hmm. Mm.
It is concept of reducing overfitting. That means if you are adding more and more regularization, my model should reduce overfitting.
Overfitting.
Okay, because I don't know overfitting. That is a concept. Now coming back to our concept, I'm saying C over here is inverse of R. Okay, that means if C value increases, R will decrease. Okay, or R increases, C decrease. Okay, the reverse of it.
Okay. Okay.
Now let's try to understand this. So when I'm saying C is increasing, that means value of C I'm taking bigger value. Okay,
Mm-hmm.
the C value you can take. Okay, so C is any number you can take. I'm saying C, for example, if you go to HSQL and SVM, okay, this is HSQL and SVM documentation. Okay, now if you see these are hyperparameters, what are hyperparameters, right? So now we'll see this code, but if you see there is one parameter called as C. Now if you come here, this could be a float
Float.
value. Okay, this could be any number, regularization parameter. Okay, so as it is saying that the strength of the regularization is inversely proportional to C. Okay, and this should be a positive number. Okay, and it is inverse to the regularization. Okay, by default
Yeah.
it will be 1. Now coming back, so what it is saying, so you can give any number, 30,
Mm.
40, 20, anything, but usually will not give, we'll give a small number.
Yeah.
Okay, yeah. So now here using this, let's try to understand. If C is increasing, that means R is decreasing.
Yeah. Means overfitting is
Yeah. Now
increasing.
R is decreasing, but what is R? R will help you, regularization will help you in controlling the overfitting.
Correct.
If regularization is decreasing, that means you are losing the control.
Correct. Overfitting
Correct?
might be
So
increased. Yeah.
overfitting
Will be increased.
will increase. If overfitting will increase, okay?
Whatever you give, it
Yeah,
will be
yeah,
correct.
overfitting will increase. So that means what? Uh, if you remember,
Our model
if the model is overfitting,
accuracy will be increased.
yeah, correct. But training accuracy, right? So
Yeah.
if it is overfitting, that means we have training and test. So
Yeah.
on training data set, it is perfectly working. So that
Yeah.
means we
Correct.
will have less bias. Bias will be
Correct.
less.
Yeah.
Okay. But on the test data set, it is not that good. So variance will increase.
Correct.
Okay. Variance will increase. Okay. Getting?
Yeah.
So that means what? On training data set, it will work very well.
Hmm.
That means uh, if you're reducing overfitting, sorry, if you're reducing the regularization, okay, overfitting is happening more.
Got
Okay,
it.
correct. I will just go through once again.
Yeah.
So
Yeah.
we are increasing the C value. That means regularization is decreasing. The what is regularization? Regularization is the method of controlling overfitting. So
Yeah.
if you have more regularization, that means it will control more overfitting. Okay. If
Yeah.
you are
Yeah.
having more regularization, that means you are not controlling overfitting.
Correct.
That means more overfitting will happen. Okay, so that means overfitting is happening. Okay, so if overfitting is happening, so it will work best on the trained data set, which is bias is will be less. Okay, and variance will be more. Okay,
Yeah.
so it since it is working very well on the trained data set, so you will have less misclassifications. Okay,
Hmm.
classifications will reduce.
Yeah.
Okay, fine. So but
Yeah.
focuses, okay, can have less misclassifications, and you will have less bias and more variance. Okay, the other way around, if you decrease C, okay, if you decrease C, the R will increase. Okay, if you decrease a lower value of C means what? A higher value of regularization. Okay, if you're having more regularization, okay, there will be less chance of overfitting.
Yeah.
Okay, if you're having less chance of overfitting, then you can have a bit more misclassifications. Okay, why? Because there is no overfitting. Okay, because there is no overfitting, that means what? It is it is working okay on the bias. Okay, but on the test data set it is working well.
Yeah.
Okay, because on training data set, I'm not overfitting, I'm giving some
Correct.
freedom to it. So
Yeah.
there is scope for it to work well on the test data set.
Test
Okay,
data set.
you will have less variance.
Yeah.
Okay, but but on my training data set, because I'm not forcing it to overfit, okay, there will be some misclassifications.
Got it.
Okay, so there will be some misclassifications. Okay, but I'm okay. That's the whole concept of soft margin, right?
Yeah. Yeah.
Okay, soft margin. What I'm saying, okay, I'm okay with some misclassifications.
Correct.
Okay, so but my variance will reduce. That means on my new data set, I will perform well. Okay, so that's why usually we take a lower value of C, like 0.1, 0.001, like that.
Okay.
Okay, why? Because if you're having lower value of C, that means what?
Regularization will
You're
increase.
using more
Overfitting will be
regularization.
decreased. Yeah.
Okay, if you're having more regularization, so there will be very less chance of overfitting. If you're not overfitting, okay, that means you will have
We will get
your
more classifications.
yeah
Yeah.
classification.
Misclassification.
Okay,
Yeah.
fine. So now what's happening here? Yeah. So here what I've written. So when we're coming seeing here, so when we're having less misclassifications, okay, that means your margin is perfect.
Hmm.
Okay, and when you are oh, one second. What is this? When I'm saying when can we can have more misclassifications? If you're having more misclassifications, means what? We'll try to understand. So one is margin error and one is classification error. Okay. So over here, when I'm saying C is less, okay, C is less. So obviously we are having more misclassifications. Okay. So if you're having more misclassifications, classification error is
Mm-hmm.
getting ignored. Can I say
Okay.
that? With C decreasing, okay, with C decreasing, I'm having more misclassification. Okay, if
Yeah.
more misclassifications means what? This error I'm having more.
Yeah.
The classification error, right? So this error
Correct.
I'm having more. That means the distances, this zeta is greater than one, right? So these points are increasing, and also these points are also a bit increasing.
Correct.
Okay, so the focus is on this. The focus is shifting on this. Focus on the
Okay.
margin error, because clearly when I'm saying C is decreasing, I'm saying I'm okay with some more misclassifications. Okay,
Hmm.
when I'm saying okay, I'm okay with misclassifications, then I'm not focusing much on this error.
Yeah.
Okay, so I'm focusing on only that. I just want to separate the maximum, the support vectors. Even there are few misclassifications also, I'm okay. That's what I'm saying.
Okay.
Okay, it's focusing on this margin. But when I'm saying, hey, I don't want that, I want very less misclassifications. Means what? I am
I
saying
mean,
this error
yeah,
should be very, very low. I
yeah,
don't want any misclassifications at all. Okay. I don't, okay, even I don't know about this error, margin error. Okay. Even if it is less or more, also I'm fine. But the classification error should be very, very less. Okay. The focus is moving to this point. Okay.
yeah,
Just an extra point I have mentioned here. But if you just understand one major thing you need to understand out of this, if this is confusing, is we will usually use a small value of c. Okay. If you decrease the value of c, okay, you will have a bit kind of, better performing model. Okay.
yeah,
Yeah, of course you will have some misclassifications. Okay. But you will have a model with less variance.
correct.
It will
That's
work
correct.
well on
Means,
the new data set.
yeah, test data
Okay.
set. Yes.
But having said this, usually we experiment with different value of c.
Okay.
0.11. I have not seen a large value of c's. Okay. But we can
Mm-hmm.
experiment with that. Okay.
Okay.
So is this clear? So we already understood this part. Now we understood zeta, what is zeta, and we understood C also.
Yeah.
Clear?
Understood. Yeah.
Okay. So now, yeah, so use on this regulation parameter, okay, yeah, we have few things. See, high C value. So what is this high C value will do? A high C value aims to minimize the training error by allowing fewer misclassifications. Okay. So just like we saw, a C increase in C value will have only less misclassifications on the training data set. Correct?
Yeah.
This what it will do, that means what, on your training data set, if you are having very less misclassifications, means what, your training data error is less, that means your
Yes.
bias is less.
Yeah.
Okay, so this reduces bias but increases the variance,
Variance.
making the model more prone to overfit.
Overfitting.
Okay,
Correct.
because on my training data set I'm reducing bias, means okay, you are working well but you're not realizing that you are unnecessarily overfitting.
Yeah.
Okay, what is the problem with that? Because on test data set it might fail.
Okay.
Okay, same thing. If high C value, you will face overfitting. Okay, C is increasing, high C value, more chances of overfitting. Okay, low value. Okay, yeah. So what is the result? The decision boundary becomes very tight around the support vector, potentially fitting noise. Okay, so same thing. So if you're focusing on more classification area, okay, that means you don't want any classification errors at all, so then you will have the overfitting. Fine. Now coming to the
Yeah.
low C value, the reverse of it. Okay, so you're
Mm-hmm.
allowing a bit more misclassifications but you will have reduced variance where it can work better, and which can prevent overfitting. Okay, but if you do more then it will underfit. Okay,
Okay.
that means if you, okay, here I'm saying I'm okay with some misclassification if you decrease C, but if I keep on decreasing C, a very small value, then you are giving more relaxation. That means initially, if you're okay with two or three misclassifications, but if you keep on decreasing C, then more and more misclassifications you are saying okay, like 20, 30, 40. If let's say out of 100 points, if 50 misclassifications, then it is underfitting. That means it is not fitting at all.
Yeah.
Correct? So that's why very small value is also not good, very high value is also not good.
Yes.
Okay, clear?
Yeah.
Okay, fine. So now coming, I think this is kind of basic concepts behind the soft margin. Okay, finally you have loss function.
Mm.
So just to summarize, every equation will have a loss function. Okay, in linear
Yeah.
regression,
Yeah.
so you have loss
Yes.
and logistic also
Yes.
loss.
Yes.
What is the
Last
healthy
should be.
of loss? Loss
Last
should be
should
minimum. Okay.
minimum.
For
Correct.
that, what we did, so just to give a recap, in logistic regression, we had a line. Okay,
Yeah.
we keep on finding new lines. Okay, but for each line, you will have some parameters like W1, W2. In linear regression, we had M and B. Okay, so for each line, you will have this, and we'll calculate the loss. Okay, and then we'll go to new line. And sorry, with that, what we'll do with the use of gradient descent, we'll calculate those parameters which will give the least loss.
Mm.
Correct? Same thing will happen. Okay, over here also, we have in the SVM, we have a loss called as hinge loss.
Okay.
Okay, the hinge loss function is simple. Okay, it will just tell you what is the maximum of 0 comma. Okay, that means if you take any particular point, okay, a particular point loss is maximum of 0 comma 1 minus yi into f of xi. where f of xi is wx plus b. Okay, don't worry. This is w into, sorry, y into wx plus b. Same thing what we have here. We have this, right? The yi into wx plus b. Our condition,
Yeah.
man. So we have this condition, right? So we clubbed these two
Double
2.3,
two and three.
we
Two and
kept,
three.
yeah, right? We got one equation, yi
Yes.
into wx transpose b. Same thing he has written in this form. Okay. So he
Oh, y of
considered
okay,
wx
okay.
plus b as f of x, and that we
Got
are
it.
doing yi. Okay. If you don't want, this is directly wx plus b.
Okay.
Okay. Clear?
Yeah.
Fine. So now he's saying for any point, if you want to calculate the loss, it is just maximum of 0 comma 1 minus 1. That what is this equation? See, when I'm saying maximum of 0 comma some value. Okay. If
Mm-hmm.
this value is 1, what is the output of this?
That is in between.
No, I'm saying maximum of
Mhm.
0 and 1. What is maximum value between 0 and 1?
Maximum value between 0 and 1. Maximum 1.
1, right?
Yeah.
Exactly. So this value, I'm saying if this 1 minus y1 f of
Okay, okay.
x, okay,
Okay.
this is 1,
Yeah.
then maximum of what will this will become? This will
1,
become
1.
0 comma 1.
Yeah.
And maximum
1.
0 comma 1 is 1. Okay. Now 0 comma, for example, this 1 minus y f of this value is, let's say, minus 2.
Okay.
Okay. Then what will be maximum 0 comma minus 2?
0.
0, right? So that is what it is saying. Getting?
Okay.
Okay.
Yeah, yeah.
Now we'll see. So for correct classification, okay.
Okay.
Now I said the 1 minus 2, etc. But how we are going to these values? We'll see. So this 0 is 0, 1 minus yi f of xi. Correct? So now
Hmm.
if we need to find out this yi of xi, if you know this, then you'll do 1 minus something and you'll get that value, and you can calculate maximum value between 0 and that value.
Okay.
Correct? Getting?
Yeah.
Yeah. So for correct classification,
Mm-hmm.
okay, my loss will be 0.
Yes.
Correct? So
Yes.
that means what? My yi f of xi. Okay. So this will be 1. Okay. Why? Because if you see uh yi f of xi, okay, this is be going to be 1 for these points, right? So if you see,
Correct separable.
yeah, okay. So for these points, you are going to have 1.
Mm-hmm.
Okay. Where I have mentioned, yeah, yi is greater than or equal to 1. But for support vectors, for the correct classification, it will be equal to 1.
Okay.
Okay. So for those scenarios, when you have this as 1, okay, when you have
Hmm.
this as 1, right? So you are going to have the value is 1.
0.
Uh, 1 second. You are following, right? Is it
Yeah,
confusing?
yeah.
Right.
No,
Okay.
no.
So I'm saying this yi w transpose xi is greater than or equal to 1 is the equation we have here, Karthik.
Yes, yes.
Agree?
Yeah.
yi w transpose x plus b equal to y. Now, for support vectors, what will be this equal to?
Support
Greater than or
vectors.
equal to, we are having greater than or equal to 1. For
Yeah.
support vectors, it will be,
I mean, that is the maximum actually.
hmm?
That is for support vectors, that will be the maximum.
No. Yeah, correct. No. See, this is for all the points. So that means this is for these points also and support vectors also. See, this is not a
Okay.
support vector.
Yeah,
This is
yeah,
not a
correct.
support vector. Only these are support vectors.
Yeah.
So for support vectors, this equation will be equal
Uh,
to 1.
okay, okay, got it.
I'm
I
telling that. Okay. For
okay,
perfectly classified values, this will be greater than 1.
okay.
Agree?
Yeah, this is for whole.
Whole, right?
Whole.
For
Okay.
this one also, for all the green points and all the blue points, other than support vectors, the value will be greater than 1
Okay.
because they're away from the margin.
Yeah, yeah, yeah.
Correct?
Perfectly already clap. Yeah.
Huh. But for the points on the margin, which are called as
Oh,
support vectors, that value will be
that is equal to 1.
equal to 1. Clear? Any doubts in these points?
Yeah, no, no, no.
Okay. Now, coming down over here, yeah, over here, when I'm saying 1 minus, we take this, yeah, when I'm saying 1 minus yi f of xi, okay, 1 minus this value, yi f of xi. Okay,
equal to
what
1.
y of xi w y, this is same as y into w transpose x plus b. Okay, so this
Hmm.
could be greater than or equal to 1, same thing, greater than or equal to this plus
Okay.
b or equal to 1.
Okay.
Okay,
Okay.
first let's consider support vector, it will be 1.
Hmm.
So 1 minus 1,
Yeah.
0.
0.
Okay, so maximum of 0 comma 0 is 0.
0.
Okay, fine. Now for other points it will be greater than 1.
Mm-hmm.
Okay, not, it will be greater than 1, right?
Yeah.
So then what will have 1 minus something greater than 1?
Yeah. Might be
What will be
anything.
this value?
Something greater than.
1 minus
Mm-hmm. Greater than 1. Yeah. Whatever
greater than 1.
negative value itself.
Negative value.
Yeah.
So
So
now,
0 will be the maximum.
what will be this 0 comma negative value?
Yeah.
What is this?
Uh,
What will the output?
0 common maximum value is 0.
0, right?
Yeah.
So we just proved for all the perfectly classified points, including support vectors,
Mm-hmm.
this loss will be 0.
Yeah.
Clear or not? If not clear, tell me, I'll explain again.
This is for uh, including support vectors. I mean, the second case.
Yeah, that for, yeah, it's okay. See, I'll tell you just once again. Okay, no problem. See here, we are having this one. So what is this? I'm just writing here. W uh, transpose x plus b. Okay,
Equal
this
to.
is the value. Okay, so
Yeah.
same
Yeah.
w, this is the value greater than or equal to 1 is
Correct.
what I'm writing here. Okay, but I'm saying this is for all the perfectly classified class. Okay, points.
Correct.
Okay, and also support vectors. If it is
Hmm.
support vectors, this will be equal to 1.
Correct.
Okay, because they are on the plane.
Yes.
For other, it will be greater than 1.
Yeah.
That's why combined I'm writing greater than or equal to.
Yeah. Yeah. Yeah.
Getting?
Yes.
Fine. Now, here I'm saying for correct, he's saying correct classifications. Correct could be this is also correct. This is also correct.
Hmm.
Now we'll
Mm-hmm.
take both the cases. So now this is maximum of this one. So just consider 0 comma something and we'll take maximum of that. Okay. Now I'm saying 0 is anyhow we are having 0 comma 1 minus, if it is support vector, what is the value of this y f of xi?
1.
1. 1. Okay. Now what this became? 0 comma
0.
0. And this is max of. Okay.
Correct.
What is max of 0 comma 0?
0.
0. Clear for this one? Clear.
Yeah.
Now again max of 0 is 0. Okay. Now again 1 minus is same. For other points, what is the value?
2.
Huh?
Let's say 2. Let's say we can consider 2.
Okay. Okay. 2.
Hmm.
Okay. 2. Now it is 0 comma minus 1, a negative value.
Hmm.
Now what is again maximum of these two?
This is also 0.
0. Okay. That means for all the correct classified points, including
Hmm.
support vectors also,
Yeah.
either
Maximum.
positive or negative.
Yeah.
Okay. You are going to get the value
0.
as 0.
Yeah.
That is loss is 0.
Okay.
Correct? Is this clear?
Clear. Clear.
Okay. Fine. Now for margin classification,
Mm-hmm.
that means what? A
0 less than.
Yeah, over
Uh.
here. Okay, if a
Yeah.
blue point is falling over here and a green point, sorry, red point is falling in this,
Mm-hmm.
that is margin classification, where the
Yeah.
zeta is between 0 to 1.
Correct.
Okay, if for blue point, if it is increasing, then it is a misclassification. For
Yes.
red point, if it is increasing, then that is also misclassification.
Correct.
Correct. Now, for those points, the value would be 0 and 1. Okay, now
Hmm.
if I do this max of 0, comma 1 minus a value, but this value is between 0 to 1.
Correct.
Okay, I'm saying 0 to 1. No, I'll write like this. Between 0 to 1.
Hmm.
It is not minus. Okay, you're getting right. 0 to 1.
Yeah. Yeah.
Okay. So what will be this?
Either it be
Yeah.
if
So
it can,
this will be, let's say this, a value between 0 to 1. Okay,
yeah, if it
between
is,
0 to 1
yeah.
is a decimal value. And if you
Mhm.
subtract that with 1,
You
this
get a positive value.
this will be a value greater than 0.
Correct.
Definitely, right? For example, let's take two extreme cases. One is 0.1, one is 0.9.
Hmm.
Okay, because it cannot be 0. That's why I'm taking 0.1. It is between only 0 to 1. And if it cannot be 1, that's why I'm taking 0.9. Okay, so now if you take 0.1, then this will become what? 1 minus 0.1.
Yeah.
How much it is? 0.9.
Correct.
Okay, the maximum of 0 and 0.9 is 0.9.
Yes.
Okay. Now if I take 0.9, 1 minus 0.9 is 0.1.
Correct.
Okay. Maximum of 0 comma 0.1 is 0.1.
Yeah, whatever the case, it will
Whatever,
be
yeah,
some
whatever I'm
value.
getting here, that is the
Hmm.
value.
Correct. That is
Okay.
greater than 0 itself. Yeah.
Correct. So that means what? What is this? This is 1 minus yi f of xi.
That is a maximum.
This is the maximum. Okay.
Hmm.
So that's why for marginal classifications, the loss will be y 1 minus yi f of xi.
Yeah.
Okay.
Yeah.
Okay. For incorrect classifications, this
Mm-hmm.
value will be what? For incorrect classification, this value will be less than 1.
Less than 1.
Right? Because for correct classifications, it is greater than 1. For incorrect, it will be less than 1. That means
Yeah.
1 minus a value less than 1.
Correct.
Okay. So then also, whatever the value you are going to get here,
Mm-hmm.
okay. So that will
Yeah.
be,
Positive value only.
yeah, right. 1
Hmm.
minus a less
You
than
can
1
take
value. Okay.
you can take minus. I mean, whatever minus 1 you can take. It will be 2.
Yeah, correct. So it will be 2.
Hmm.
And if I take 0.5, so it will be 1 minus 0.5. It is again
1
greater than.
point. No, 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 no. It will be less than value, right? So 1 minus in
Oh, I'm
bracket
saying
also we
less
have
than 1, not less than 0. 1 minus,
less than 1.
yeah, less than 1 is 0.5.
Yeah,
0.5.
yeah, less than, yeah, correct, correct. Less than 1. Sorry.
Okay. So 1 minus 0.5 is what? 0.5.
Point 0.5. Yeah,
So again, maximum of 0, comma 0.5 is 0.5.
correct.
Okay. See, less than 1 means you can start with 0.9. Okay. You will have
So,
0 here and all negative values.
yeah, yeah,
Okay. You take
yeah,
any negative value, it will become positive.
yeah.
Anyhow,
Correct. That
that
is
is greater
also
than
mentioned.
0.
Yeah, yeah,
Okay. You take any value in between here and you subtract 1 minus that value, that will be again greater than 0.
correct.
Okay. So that means again, whatever the value you take this 1 minus, that is this value. 1
Yeah,
minus y of xi. Getting
yeah, yeah.
clear?
Hmm.
So now finally the final loss equation. Okay.
Mm-hmm.
What we have is we club these two. So the
Yeah,
final
got it, got it.
minimum of 1 by this is the one. Okay.
Mm-hmm.
And C of, okay,
Mm-hmm.
C is our parameter. Okay. And we already have instead
Yeah,
of zeta, right? Zeta is what it
yes,
is saying. Zeta is talking about the distance. Okay. The
correct.
distance we are writing in a different form. Okay. How
With the
far?
minimum.
Okay. 1 minus yi z. Okay.
Hmm.
Correct. So we use this equation. Okay. Maximum 0, 1 minus y of xi, right?
Hmm.
Okay. So we use this. Okay. C,
Got it.
yes, C, but maximum of 0, comma 1 minus y of yi. See here, he wrote exactly. Okay. Y w transpose x plus b.
Yeah.
Okay. So earlier we have this zeta, but zeta is what? Zeta is talking about the distances. How
Yeah.
far,
So
how near. Same
same
thing here
distance
also
with the
we are
minimum,
discussing.
minimum distance.
Because inside this only the zeta is operating, if you see.
Correct.
Correct? For correct classifications, okay, the zeta is also 0, I think. Okay. If you see, for correct classification, zeta is 0.
Yeah.
For incorrect, it is 0 to 1. Okay. Using this only, we created this function. Okay. So when we
Yeah.
club these two, so this is the final loss function, Karthik. Okay.
Hmm.
So we want that plane. So now to summarize, we want that plane which first it will minimize this one.
Hmm.
Okay. Minimize the, we'll get a minimum value of this. That means, what do I mean by that? That means whatever the plane you are having, I don't know, 3 dimension, 4 dimension, W1, W2, W3. Okay. That square when you do and divide by 2, that value should be minimum. Okay.
Yes.
And also, but
Distance should be minimum.
yeah. So maximum of, uh, see, first of all, you will take the maximum of this value and you do the summation of that. Okay. Summation of that for each individual value. But again, overall, also you want the minimum.
Yeah.
Getting?
Yes.
Okay. See, this is anyhow you want minimum. Okay.
Hmm.
Here, while calculating, you will take the maximum value. That means for point one. So see, here you are having 10 points, 10 points, 20 points. You will take this first blue point. Okay. You will while calculating this one, you will take the maximum value of that. For green point, you do this operation, you take the maximum value, you will get some value.
Yeah.
And again, for second blue point, third blue point, so first green point, like that, you for 20 points, you will do this.
Yes.
Okay. Whatever the overall value you are going to get, that should be minimum.
Yeah.
Okay. Because this is overall loss.
Correct.
Correct?
Correct.
Yeah. Because why? Because if you try to understand here, this anyhow this we understood. Okay. I hope this part this is
Mm-hmm.
discussed nicely.
Yeah.
Now coming to this part, for correct classifications, anyhow this is becoming zero.
Yes.
Okay, this is becoming zero. Okay, we don't need to do anything. But for incorrect classifications only, or at least margin classifications, the loss is becoming 1 minus yi f of xi.
Mm.
Okay, so this is becoming correct. So when you add so many of that, all of those are what? Those are errors.
Correct.
Correct. Those are all errors. When I'm saying this much, 1 minus, all these are errors. Error should be less.
Yes.
So finally, the overall value of this plus this, whatever you are getting, that should be minimum.
Yeah.
Okay,
Mm.
clear?
Yeah.
So that means what? Let's say you have 10 planes, random planes
Mm.
I gave you. First plane you will
Correct.
take. Okay. You
Yes.
have the equation, some equation. Okay.
We
You
will,
take
we
that
will get
plane.
the we
Yeah.
will get the
You
some value.
calculate this. Yeah. You will calculate this. That means the plane equation W1, X1, W2, X3, W3, X3, for example. Okay. W2, X2. You will take this W1, W2, W3. You will do this mod of this. You calculate. And for this plane, you will take all the 20 points. For each point, you will calculate this. Okay,
Mm.
and you will you can consider some c value. C is a constant. Okay, initially you can consider an experiment and find out. Okay, but you will using this w's, you will get this value, and using calculating for each point this value, you will get some value. You will add this. That will be the final value of plane one.
Yeah.
The value like that you will do for plane two, plane three, like that. If you have 10 planes, you will calculate all those distance for 10 planes.
Yeah.
Which one is giving you the least value?
Minimum. Minimum. Yeah.
That is the perfect one. Clear?
Clear.
Okay. Now, as I told you, this is the loss function, and we want those parameters or those W's which will give you the least loss.
Correct.
Okay. So now, same concept we are going to apply.
Mm.
We say what we studied: linear regression, logistic regression. We have loss function. Our whole aim, okay, the overall aim of us, our overall goal is to find out a loss function, Karthik.
Yeah.
Because we already have our friend gradient descent ready. Okay, he's just asking for equation, and he will give you the parameters which will give you the least loss.
Okay.
Correct? That is his job in linear regression also, in logistic regression also. He's doing
Correct.
the same thing. He's just telling,
Correct.
give me the equation, loss equation. Okay. And I will give you those parameters for which you will get the least loss. In
Yeah.
linear regression, we got M and B.
Mm.
Correct? We want those parameters M1, M and B, which will give you the least loss. Okay.
Yes.
And logistic regression also, we got the W1, W2 for least loss.
Mm-hmm.
Gradient descent is
Yes.
doing. So I told you this 10 planes, right?
Yeah.
We do for it. So in reality, we are not going to do that. Correct?
Correct.
How many planes we will calculate? So we
Yeah.
are just using our gradient descent. Okay. We will say, hey, this is my loss function. Start with some random plane. Okay. Some random plane. Okay.
Mm.
And do your operation and finally give me that plane which will
Mm.
have the minimum value of this.
Yeah.
Okay, so what it will do, see the overall what all we studied in last session and this session is simple. Okay, to find the best hyperplane, what we'll okay, so what we'll do, we'll take some plane. Okay, and the aim is to have the maximum margin. Okay, so for that we will find out the loss function.
Correct.
Okay, we got the loss function, that's fine. Okay, now using this loss function, we will calculate the predictions. Okay,
Mm.
okay, that means see, when I'm saying some random line we'll take, Karthik. Okay, some random
Yeah.
plane. Okay, some plane.
Yes.
So with this plane, obviously, this when I'm saying plane, that means this should have some equation.
Correct.
Okay, let's say this is the equation Wix, some equation. When I'm having this equation, easily I can calculate the loss.
Mm.
Okay, how I'll get the loss? Because I'll use a
May,
yeah,
correct.
because I have the equation, I can simply do the prediction. I will see which side of the plane the data point is falling. Okay,
Yeah.
with that I'll get loss as 0 or plus greater than 1 or in between 1 or greater than 2 or something like that. Okay,
Yes.
like that you will have the loss function.
Correct.
Okay, so and if you have that loss function, okay, you will get some parameters. With that parameter you will get a line. Okay, with that line you will do the prediction. Okay, and if it is fine, it's okay. Or again from that you will calculate, you will go to new values of W and B.
Mm.
Okay. Oh, here in the case in yeah, we have the B also, right? Okay, yeah.
Yeah,
It is not passing through origin, B also. So just to summarize, we'll start with some
random plane.
random W and B values. That means random plane we have. Okay.
Hmm.
So using this plane, using this plane, we will do the predictions.
Yeah,
Okay. So here some points, you do the predictions. So
yes,
obviously predictions will give you some loss. Okay. We can
yes,
calculate the loss using this equation.
yeah,
Okay. So now you have that loss. So now what we are saying, we started with some random plane and we have some loss. So, but the loss is not minimum. We can reduce this. So what it will do, it will go to new values of W.
correct.
Now
New
W
plane.
equal to W old minus learning rate of dou L by dou W.
Ah,
Same thing we studied, right? So if you see
true.
the gradient descent, see, that's why I said once you study, it's same thing. For yeah, if you see M and B, M new equal
Yes,
to M old minus learning rate into slope. What is the slope?
slope.
Dou L by dou.
Correct.
Uh, right? Yeah, slope is dou L by dou M. Correct? And for B,
Hmm.
dou L by dou B.
Correct.
Correct? Same thing. The gradient descent concept will not change. So here also, this loss function. What is this? But for, yeah, so this is the main thing. So to do this our aim is to do this. Okay.
Hmm.
So our aim is to just do this, and also for B also you will have B's old minus learning rate into dou L by dou B.
Hmm.
Correct. So we just want this for the if you have
Correct.
this, the gradient descent will directly give you do some experimentation and will give you the best values of W and B such that this loss function is minimum. But to do
Yeah,
this, you need this L. You see. Okay, you need this L. L is what? L is my loss function.
yeah.
So that's why we want this loss function. Okay, that's why we
Okay.
derive this loss function. So now,
Okay.
since we have this loss function, we'll just give this to gradient descent. So it can calculate this derivative. Start with some random value. This random value will become this old value. Okay, from this old value, how it will go to new value? Use this whatever the random value you took, that value minus learning rate. Learning rate you can take like anything 0.1 something like that. Take this function, do differentiation with respect to the old value, you will get some value, put that. Okay. So
Okay.
let's say you started with some W0 equal to 10. Okay. From there, you will go into some new value will be some 12 like that. Okay.
Okay.
Slowly, new values will be. And when you have a new value of W and a new value of B, that means you have a new plane.
Correct.
With that plane, again, same story repeat. With that plane, again,
Hmm.
find the predictions, get the loss,
Yeah.
minimum, again, do the differentiation, go to new plane like that. It will do certain permutations, what is called certain repetitions. After that, it will give you those parameters of W where the loss is minimum.
Okay.
Clear?
Yes,
Any
Santosh.
doubts?
No, no.
Okay, fine. So I would say that concludes most of the theory of SVM.
Hmm.
Okay, so we saw with the basic equation and hard margin, soft margin, everything. Okay,
Yeah.
and a small scenario also we have seen if given multiple planes, how you can find out.
Hmm.
Okay,
Hmm. Hmm.
so then
Yeah.
only if you code, then we have code session. So we'll see next class. So which is very simple. Okay, so code is nothing to worry, and hyperparameters assumptions, everything is fine. Okay, the only one important thing, okay, and which the SVM is very famous also is called as kernel trick, Karthik. Okay, kernel
Hmm.
trick. That is one of
Okay.
the very special character of SVM. That means this we'll discuss in the next session. Okay. But
Hmm.
just as an idea to give you is, so if you are having, so the idea of kernel trick is, to, if given a data set in particular, let's say 2D, okay, it is
Hmm.
able to transport it into a higher dimension.
Okay.
Okay. And then it will do the division.
Okay.
Okay. So for example, if you're having all X, okay, is one data set and zeros or some, okay, in the middle of that. So now if you able, if I ask you, this is a 2D, if I give you a line to divide, so no line can divide correctly classified.
Correct. Hmm.
Agree? In this case, assume what it will do is it will try to, okay, uh, what do you call,
Project.
it will consider these data points and it will create new values for these data points in higher dimension.
Okay.
Okay, so that means it will in one plane you will have the x data points, and in a upper plane you will have the zero data points because it is now in the
Okay.
new dimension. Now it will
Okay.
in these two places it will try to cut with a plane.
Okay.
Okay, so that's called kernel trick. Okay, so it's
Hmm.
just I'm giving a brief intro, but In the next class, we'll see what is kernel trick and how it is able to do that. Okay. So, and this is the
Okay.
special character of SVM. No other model have this. Okay. Or
Yeah.
decision trees, logistic, no other model have this. Only SVM have this kernel trick. Okay. That's why it's very, very famous. And that's why it works very well with higher dimension data also.
Okay.
Okay. So we'll see that. Okay. But that is in next session. So that and the code, these two are pending. But apart from that, the basic concept about SVM is this. One thing you need to remember is hard margin and soft margin. And once you have the loss function, the same story repeats. Nothing much. Okay.
Okay.
Any doubts?
No, Santosh.
Okay, fine. So that's all for today. Let's meet next class.
Yeah.